This example is a second-order circuit case. In the second-order case, we have two storage elements. Here, the inductor, the 1 Henry inductor, and the capacitor, the 0.1 farad capacitor. But in essence, when we have a second-order circuit and we solve the circuit, then we obtain a second-order differential equations. By the way, this is a significantly more complicated mathematically as compared to the first order and, of course, to the DC circuit, because we're dealing with the solution to a second-order differential equations. This is also a case where we have what's called a source-free circuit, because we have the source is connected. For t less than 0, it's connected to the right hand of the circuit, and of course at t equals 0, the right part of the circuit becomes disconnected and we have a source-free circuit. So we expect to have a differential equation that's homogeneous with a 0 right-hand side. Now, anytime we have a switch here at t equals 0, we solve the circuit before the switch action and after the switch action. So in this case, we're going to solve the circuit for t less than 0 and for t greater than 0. We never solve the circuit at t equals 0 because the circuit is undefined. Now, in many of these examples that we have, the first time period is typically a DC circuit, because in the first time period we assume that the circuit is being connected for a very, very long time. Thus, the inductor has not seen a change, neither has the capacitor. So in essence, we're going to say for t less than 0, the inductor behaves like a short circuit, and we're going to physically replace it by a short circuit, and the capacitor behaves like an open circuit. And this is going to be a DC circuit to be solved. So for t less than 0, this is what we got. I replace the inductor by a short circuit, and the capacitor, just remove it, and it's an open circuit. Now, clearly from that picture, we can see that VB is 0, because VB is the voltage across the inductor, and it's a short circuit for t less than 0. Now, you are asked to calculate VB, and we could answer that question right now. But folks, you need to have the inductor current and the voltage across the capacitor. Now, it's up to you, the polarity of that voltage across that capacitor and the direction of that current. However, you need those values, because they are the initial conditions for the time period t greater than 0. So even though you're not asked those quantities, you absolutely need to find them. So we have to solve the circuit here, if nothing else, to find VC and IL, because we already know VB. It's kind of explicit from that case. We're going to use mesh. This is a case where we have two finite meshes. Now realize that the third mesh, that's where the capacitor is, it's not a finite mesh because it has an open circuit, which is why we don't put a current on it, because the current obviously is 0. But this is a standard DC circuit, of course, with a dependent source. Nothing dramatic here. I put my two mesh currents, I1 and I2. Of course, IL is equal to I2 here, so I could have called I2 IL. And then I'm going to go and solve for I1 and I2, and then if I know that, then I can solve I2 is IL, and realize that VC is actually V2. So solving that, I get all the information. I also put voltage polarities on the resistors that didn't have standard things for DC circuits. First thing I do, I write the dependent source in terms of the mesh currents. So I2 is equal to 2IA. And that's pretty much my first equation. All I have to do after that is express IA in terms of I1 and I2. The second equation comes in KVL in the meshes. Of course, we only have one real mesh, one mesh here, which is I1. So KVL in mesh I1, it's V1 plus V2 equal 8. And after that, we go right out to Ohm's law to express those voltage in terms of the mesh currents. Here are the Ohm's law equations for V1 and V2. And of course, IA, we express it in terms of mesh currents I1 and I2. So it's simply I1 minus I2. So we take those equations, we pour them all into the source and KVL equations, and voila, we solve for I1 and I2. Of course, we are going fast here because this is assumed to be understood and well practiced by now. We get two equations, two unknown, solving for I1 and I2. and the values for I1 and I2, and then of course I2 is equal to IL, and VC is simply V2. So, and VB, we know that VB was 0. Now, the values for IL, which is 0.106 and VC, are going to be the initial condition for t greater than 0. Of course, the initial condition at t equals 0. So we're going to need to use those in the latter time period. This is the part that really is different from what we've done before, in terms basically solving the circuit for time period t greater than 0. Now the switch essentially opened up, so the capacitor and the inductor now have seen a change, so they behave like capacitors and inductors. No longer short circuit and open circuit, so you have to put them back in. In any transient problem, in my view, the main objective has to be to calculate the ordinary differential equation. Now, after you do that, you can find the solution. But I'm going to look at the differential equation as a main gateway for your partial credit here. I'm going to use mesh here again. We have 3 meshes, which are labeled I1, I2, and IL. IL being obviously the current to the inductor. Notice that the polarity of my VC and the direction of my IL has to remain the same as the previous time period. You can't flip things around. And I'm just going to carry a standard mesh at the beginning, and I'll show you now how do I bring in the inductor and the capacitor into the mix. Of course, we have a source, a current source. It's a dependent current source. First thing we do is write it in terms of the mesh currents. So we got I1 minus I2 equal to IA. That's going to give us our first equation after we do Ohm's law for IA. Where are the next equations coming from? We have what we call a regular mesh in mesh IL because there are no current sources. And of course, we have to do a super mesh between I1, mesh I1, and I2. So KVL in the regular mesh, VB minus V2 equal to 0. And then we do a super mesh for I1 and I2, and that's minus V1 plus V2 plus VC equal to 0. The super mesh, of course, it's looking at both mesh I1 and I2 and removing or ignoring the common branch. The common branch here is where the current source is. Okay. Now, this is where I ask you folks, and I ask you to follow that rule to write your KVL equation in terms of voltage, and if you're doing nodal, to write your KCL in terms of current, because things get very complicated as we're dealing with inductors and capacitors in the transient problems. Okay. At that point here, nothing that we've done is different from what you've been doing for DC circuit. Things are going to start changing, but the first thing we're going to do here is use Ohm's law, write all for every resistor in the problem. So here I write my Ohm's law equations for V1, V2, and of course I express IA in terms of I1, which is simply IA is equal to minus I1. But basically, I write Ohm's law for every resistor, and then I'm going to use these Ohm's law as equations into the previous 3 equations that we got. So for the time being, folks, I'm asking you to ignore, forget about the capacitor and the inductor. Don't deal with them yet. Let's deal with the resistors, put them in, and look at the 3 equations that we got. So I'm going to take those 3 equations that we have here, stick them into the 2 KVL and the source equation, and come up with 3 new equations. So we do that, and we have our 3 equations. All those 3 equations they are for the source, for the dependent source, the KVL for the super mesh, and the KVL for mesh IL. That's the 3 equations that we have, having used Ohm's law for V2, V1, and having used IA equal minus I1 into these equations. At that point, we're going to start dealing with the inductor and the capacitor. Okay, but up to that point, you should all be able to get there. There's nothing different here. Now, what I want you to do is step aside and write the voltage current relationship for the capacitor and write it for the inductor. Now, folks, don't give me generic equations. Don't give me equations that mean nothing. Don't give me VL is equal to L di dt. I don't have VL here. I don't have L here. Well, give me the equations for the inductor in terms of what we got in the circuit. Okay? And also, you better know the voltage-current relationship for an inductor and capacitor. Don't swap them. They don't change depending on the problem that you're facing. Okay? For the capacitor, what is the current to the capacitor? It's I2. Is it going against or following the passive sign convention? It's following the passive sign convention because it's entering the positive sign. So I say I2 is equal to 0.1 farad, which is the capacitance, times the derivative of the voltage, which is Vc. For the inductor, the voltage across the inductor, which is Vd, is equal to the inductance, which is 1, times the derivative of the current, because the current is entering the positive terminal. No generic equation. We write equation according to what we got. I don't want you to be essentially to be putting down quantities that don't exist and makes the problem even more complicated than it already is. Now the question comes in. How do we bring these two equations into the three equations that we got? Folks, when we're dealing with second order, very often there is an order in which to bring these capacitor and inductor equation. What do I mean by order? I mean that you may bring the capacitor equation first in all three equations, and then after that bring the inductor, or vice versa. The order becomes important. If you look at the equation for the current, for the capacitor current, and the equation for the inductor, see if those two equations are coupled. What do I mean by coupled? See if you have one parameter in the top equation that belong in the second. If they share a parameter, that means they're coupled. In this case, the top equation has I2 and Vc. The bottom equation has Vb and IL. They don't share any parameters, so they're not coupled. So there is no order. You can bring in both of them at once. You don't have to follow an order. So what I'm going to do here in those three equations, wherever I have I2, I'm going to stick in 0.1 dVc dt, and wherever I have Vb, I'm going to stick in dIL dt. And I'm going to come up with three equations. And here they are, just doing them. You're almost there. The rest is just going to be manipulation. Now, we have those three equations here. How do we deal with them? Basically, we have to use the method of substitution to come up with one equation, one unknown. And it's going to be a differential equation. So, for example, if I look at equation, the top equation, I can see that I can solve for I1 in terms of Vc. And if I do that, then I can stick in for I1 in the other two. That's what I do. I solve for I1 and I stick it in the other two. So now I'm down to two equations, but I don't have I1 in my problem anymore. So now at this point here, what can I do? Well, in the second equation, which you have at the bottom of the screen, I can solve for IL and write IL in terms of Vc. And of course, if I can do that, then I can use that result for IL, stick it into the first equation, and I get my second order differential equation. And that is the procedure. When you get to those three equations, it really takes some practice and some nerves, because many times students get confused as they have those three equations or two equations, what have you, and they have to combine them to get one differential equation in terms of one unknown. And many times you lose poise in doing so. So practice is really what gives you confidence in doing that process. So here we solve for IL using the second equation, and then we're going to stick it into the first at the top of the screen. And of course, we have our second order differential equation, and it is traditional that we normalize that differential equation such that the coefficient of the highest order derivative is 1. So this is, of course, an homogeneous differential equation because we're dealing with a source-free case. Even though you have that dependent source, that dependent source still makes it a source-free. You have to have an independent source to have a differential equation with the right-hand side that is non-zero. Now I'm going to slightly talk about how do we deal with those differential equations, the second order differential equations here. Now, I'm not interested in teaching you differential equations. So what I want you to do essentially is be able to write the solution once you get to that stage. You get to a differential equation that of second order. I want you to identify for me the damping coefficient, alpha, and the natural frequency, omega sub n. And the damping coefficient is the coefficient associated with the first order derivative divided by 2, and the natural frequency, omega n, is the square root of the constant associated with the term with Vc here. So you identify those terms. So you tell me, in this case, alpha is 23rd, omega n is 4.47. Then you basically tell me, are we dealing with an overdamped, underdamped, and or critically damped? The overdamped case is the case where alpha is greater than omega n. The critically damped is the case where omega n is larger than alpha. And of course, the underdamped is the case where omega n is greater than alpha. And the critically damped is the case where omega n is equal to alpha. Now, each of those cases have a different form of solution. In this problem, we're only going to see the overdamped solution. But you should be able to write the solution no matter which case that we're dealing with here. We're dealing with the overdamped case. So we write the solution as basically the sum of two exponents, two decaying functions, and the values that you see here, the 1.72 and the 11.6, are the roots of the characteristic equations. So, and they are the S values that I'm showing here. So all that we have left at this point is use the initial condition on the capacitor voltage and initial condition on the inductor current to solve for A and B. Of course, I say that's all we have left, but it takes some doing, particularly to calculate IL from VC here. But realize that we need two conditions because we have two constant A and B, and we're going to have to express IL in terms of A and B. We can't apply the condition on VC and then use it after that. So here, I have VC, which I rewrite again at the top of the screen. Sometime back, we solved IL in terms of VC when we were manipulating the KVL and source equations to get the differential equations. We had IL is equal to 0.5 VC plus 0.05 dVC dt. So we have to take that equation for VC, use it, and calculate IL, and that does take a little bit of algebra and math, so you're going to have to be careful. But having done so, we come up with a value for IL, which is 0.414A, and so forth. Now realize it is in terms of A and B, because we don't know A and B until we get that IL. At this point, I am going to apply the initial condition for VC and the initial condition for IL, and then I'm going to get two equations, two unknowns. The unknowns here are A and B. So I use VC at 0 is equal to 0.053, and IL at 0 is 0.106. Stick into those two equations, solve for A and B, and of course I can now write VC and IL in complete form without these constants. They are now determined. Of course, the problem is basically solved because what you were asked to begin with is to calculate VB. VB is simply the derivative of IL. If I know IL, I can simply take the derivative of IL and I get VB, and that concludes the problem. This is, as you can see, fairly complex process, and I'm not sure how to make it even simpler, which makes it even better case for why practice is needed for these second-order equations. The key thing here is to start your method just like you do it in the DC, deal with the resistors and Ohm's law into either the KCL equations if you're doing nodal or KVL, and then bring in the capacitor and the inductor. After that, you got to basically pay attention and you got to be organized, otherwise things get confusing and you're using equations more than once.